Okay, so Reshmi asked me just to introduce Ruizhi, which is my pleasure. Ruizhi, or Professor Ruizhi Yang. So, in fact, Professor Ruizhi Yang is really young. He was a PhD student 10 years ago in Purple Mountain Observatory. This is one of the central places in cosmic ray studies in actually China. And then, but he got the very prestigious award, this Academy of Science of China and Max Planck Society, and moved to Heidelberg. So he, during 3 years, his PhD, he was in Heidelberg in Heinz Astrophysics group. And after that, he moved to China, but returned as a postdoc to Heidelberg, to same group for 5 years. Ruizhi was extremely productive, and he is very strong in analyzing almost all instruments you know relevant to Heinz astrophysics, X-rays, not only the standard ones like Chandra, XMM, but also New Star. He published a lot of very important papers using the Fermi data. And he was a principal co-author of this seminal his paper on pevatrons in galactic center. And then, and he was also is doing a lot of the result independent of data. So he's really good to characterize. Ruizhi is a very independent researcher. So after these 5 years, he got another now extremely prestigious award. It's called 1000 Young Talents, this Chinese program. And through that program, he moved to the University of Science and Technology and Science of China. This is one of the best universities in China, actually the worldwide now, especially in research. And he's a now research professor at this university. And finally, he's working on different programs. And what is relevant to this talk, he's a convener of the of this working group on stellar clusters. So one of the key working groups, as you can imagine. And now it's just a pleasure to invite Ruizhi to deliver his talk.
Okay, thanks for Felix's introduction, and thanks for the organizer to give me such a chance. Now I will share my screen.
And let me just remind everyone that we will be recording the session. I hope that's okay.
Okay.
So be careful.
So can you see my screen?
Yes.
Yes.
Okay. So let me start. Yeah. So the topic of my talk is about the recent status and the highlight of the results of the LHAASO. So this is the outline of my talk. There are 3 parts. So at first, I will introduce briefly the LHAASO detectors and the current status. And then I will introduce some of the highlight of the recent LHAASO results. And at last, I will introduce some prospect for the LHAASO and the future project of the gamma ray astronomy in China. So LHAASO is the abbreviation of the Large High Altitude Air-Shower Observatory. The collaboration is quite large now. It contains more than 200 scientists from 32 institutions and from 5 countries. Although most of them are Chinese now, but the international collaboration is always welcomed. So where is LHAASO? So LHAASO located at the east rim of the so-called the Qinzhang Tibet plateau. The altitude of the site is more than 4,000 meters. It's located in the Sichuan province. It's a mountain called Haizi Mountain. And although it's in this very high altitude, but in fact, the transport is relatively convenient. it's only 10 kilometers away from this Yading airport, which is the highest airport in the world. So it's quite nice. It's also quite nice place for sightseeing. This is the layout of the LHAASO array. It contains 4 different types of detectors. First, we have more than 5,000 electron detectors. It's made of scintillators. And we have more than 1,000 muon detectors. And thirdly, we have more than 3,000 these water chemical detectors, which are deployed in these 3 very huge water pools in the center of the array. And at last, we have 18 wide field of view Cherenkov telescopes. The total, the array cover a total area of more than 1.3 kilometers squares. These 4 kind of detectors, they constitute 3 sub-arrays of LHAASO. The first one, and each of them cover a specific energy range in both gamma ray astronomy and this direct measurement of cosmic rays. The water Cherenkov detector array is the 3 huge water pools in the center. They are mainly designed for the very high energy gamma ray astronomies. It's quite similar, but significantly larger than Hawk Club experiment. And the muon detectors and the electron detectors, both of them are combined, and we call them the kilometer square array KM2A. They are mainly designed for this ultra high energy, which is above 10 TeV gamma ray astronomy, and of course, both this WCDA and KM2A can be also used to measure the air showers from the cosmic ray events. And together with the WFCTA, which is designed to measure this longitudinal shape of air showers of cosmic rays above 10 TeV. So this means this LHAASO can also have a very good sensitivity for this direct measurement of cosmic rays, especially at the energy range of the knee. So this is a picture of the realistic LHAASO site. So this is in winter, there's a lot of snow, so we can see there are in the left, there are blue this is blue boxes. They are this wide field Cherenkov telescopes. This is one of the telescopes. We have 18 of them. And this in the middle, this under the roof is 3 very huge water pools. This is the WCDA. And the white mount covered by snow, you can see a lot of them. This is the muon detector, and this small green box is the electron detectors. So as an extensive air shower detector array, this one of the advantage of such kind of detector is the very high duty cycle. For LHAASO, the duty cycle can be approximately 100%, so it can be used every time of the year, and it also have a very large field of view. And in the left bottom figure is the comparison of the LHAASO field of view with other instruments. We can see it's similar to Hawk, of course, but compared with this Cherenkov telescope arrays like Magic Veritas HAAS, it's much larger. It can cover the 1/7 of the sky at any time of the day, and every day it can cover 60% of the sky. So one of the most the biggest challenge of the ground-based gamma ray astronomy is the so-called this background rejection power, because we know on Earth the total flux of cosmic rays is much higher than that of gamma rays, and so the ability to separate these gamma rays from the cosmic ray events is crucial for the sensitivity of such kind of detectors. So here is the schematic view of the air shower of the two different types of air showers. In the left panel is the so-called electromagnetic shower. We can see the main physical process in this in the development of this air shower cascade is pair production and Hampshire talon. And in the ground level, what we observed, the main content of the particles should be gamma rays and also the pairs. But for the right panel is for the cosmic ray shower. We know there are hadronic interactions, so there are a lot of pions. As a result, there should be quite a lot of muons also in the ground level, in the ground level where we observe the lateral distribution of air showers. So these differences can be used to distinguish this proton and the gamma rays. So this is one example of the WCDA gamma events and cosmic ray events. We see for WCDA, we don't have this. I mean, for the water chilling curve, we cannot measure the muon directly. But in this case, we can use this morphology of the air showers to get such kind of separation. We can see from the left top panel is the example of gamma ray showers. The image is much more compact, and for the left bottom is the example of a proton, the cosmic ray shower. It's much more extended and very clumpy. So currently for WCDA, we are using this a parameter called compactness to do such kind of gamma P separation. And of course, in this field, is Hawk collaboration indeed have made great progress, and we are also learning from them, and we are also trying to use both morphology parameters like compactness and pinkness, and maybe later even more these morphology parameters to do such kind of separations, which can we expect this can increase the gamma P separation power significantly. And for this KM2A, because we have a lot of muon detectors, this task is relatively easier because we can count this number of muons in the air shower directly. If it's a gamma event, the number of muons should be very small, and if it's a cosmic ray event, there should be quite a lot of muons. So this is the current cut parameters we are using, the selection criterion. We just use the ratio of muons and this electrons detected by our KM2A array. And with this simple algorithm, the cosmic ray background rejection power can be as high as 10 to 5, about 100 TeV. So from this figure, it's more clear. We just count this number of muons and the electrons detected, and you can see from the curve is the rate of observed the rate of cosmic ray event and before and after is cut. So we can see above about 100 TeV, the rejection power is about 10 to minus 5. So this means only 1 in 100,000 cosmic ray events will be misjudged as gamma rays, and above 100 TeV, this rate is much lower than the bright gamma ray sources. So in this end range, we are indeed already in a background free regime. So due to this very high background radiation power and the very large effective area of more than 1 kilometer square, LHAASO have a very good sensitivities above 10 or 20 TeV. So in fact, it's at least 1 order of magnitude higher, about 20 TeV than any other instruments. And even compared with CTA above 20 TeV, LHAASO also have a very better sensitivities. Of course, in this figure, I think this is for 1 year for LHAASO and 50 hours for CTA. But if we're considering the much higher duty cycle and the much larger FOV of LHAASO, so such kind of comparison is not so unfair. So it's and the angular resolution of LHAASO KM2A now is calibrated by the direct measurement of Crab Nebula. We found the measured angular distribution of Crab Nebula is in good agreement with our simulation results. The angular resolution in lower energy range for KM2A, which I mean lower is the energy smaller than 40 TeV. The angular resolution is about the sigma. I mean, if we fit the PSF with the Gaussian, the sigma of Gaussian is about 0.3 degrees, and above 100 TeV, this can be as good as 0.2 degrees. The angular resolution of this LHAASO, this kind of extensive air shower areas, is significantly worse than this IACTs like HAAS and CTA. And I think we still have a lot of room in this in angular resolution, because for now the angular resolution is only modeled by a Gaussian, but probably the tail is even more complicated than Gaussian. And for energy resolution, it's also quite it's good enough. So for this, of course, it depends on the Janus angle, but for this low Janus angle events, it's as good as 20% at 20 TeV, and increase to less than 15% above 100 TeV. And above is the brief introduction of the LHAASO. And so then I'll move on to the some recent results. One of the most important scientific objective of the LHAASO is to find the so-called pivatrons. So this is the spectrum of direct measurement of cosmic rays. It's the current consensus that at least to the need to about 1 PeV, the cosmic rays should be accelerated by the galactic sources. So searching for the galactic sources which can accelerate cosmic rays to at least PeV is a quite crucial task for current cosmic ray science. And in fact, it's relatively straightforward to do such kind of work in gamma ray astronomy. This is an example. This former work done by HAAS collaboration. They are trying to find such kind of hard gamma ray spectrum in some sources. And the principle is quite straightforward. In this energy range, the gamma ray production mechanism is either from a pion decay or from inverse Compton. But if the inverse Compton dominates the if the gamma ray production mechanism is the inverse Compton, in this energy range, the Claire-Nishina effects will inevitably play a role, and the spectrum will have a cutoff or softening. So if we found very hard gamma ray spectrum without any sign of cutoff or break up to more than, for example, 25 TeV, it's quite safe to claim it should be produced by protons with the energy up to PeV. So HAASO collaboration did quite a lot of network in this direction. So this is one example. This is for the source HAASO J1641. You can see in this source, there are already some hint of the existence of pivotrons, but because the HAASO, the measurement of this source by HAASO only extends to about 20 TeVs, so we cannot draw a definite claim from this source. But if it's easy to imagine if we have we can extend the measurement to higher energy range, maybe we can make a good progress in such field. So as I mentioned before, about 20 TeV is just the advantage. It's where LHAASO can play an important role. So this first 11 months data of the half KM2A array, we scanned the galactic plane, and we already found more than 12 ultra high energy gamma ray sources. These sources are all detected by more than 6 sigma above 100 TeV. So because we already observed more than 100 TeV gamma rays, so those sources should be definitely pivotrons. But currently, we cannot tell whether they are electron pivotrons or gamma ray or hadronic pivotrons. And it's also a quite exciting results that for is that our galaxy, it seems that our galaxy are full of such very powerful gamma ray cosmic accelerators. Because this is only 11 months of the half KM2A array. If we have the full array and explore for several years, we expect even more detection for such very powerful particle accelerators. So this is the table from our published paper, and these 12 sources are basically all in a galactic plane. And for two these sources, we detected the gamma rays even above 1 PeV. So the first one is it's J0533. This is Crab Nebula, and another is the Cygnus region. In fact, this is the highest energy photons ever detected. It's 1.4 PeV. So let's have a closer view of this event. This event, in fact, is quite from the experimental point of view. It's a quite nice event, because you can see here the detected the electron number detected is of the air shower is more than 6,000, and the muons is only 6. So it's quite safe to claim this is a gamma ray source. The gamma ray event. It's highly significant. And for the 3 brightest sources we detected in the galactic plane is, in fact, is already a quite famous source in TeV astronomy. They are all detected by either HAASO or Veritas or MAGIC. They are 2226, 1908, and 1825. And we found some interesting feature of all these sources. All 3, they reveal a clear spectral softening above 100 TeV. So this means we cannot use the method I used before, used by HAASO collaboration to identify this whether are proton pivotrons. But the softening is quite gradual, and we didn't find the significant cutoff, even above 200 or 300 TeV. And another thing is all these 3 sources are extended. This is also in consistency with the former measurement by this Air Telescope arrays. And unfortunately, or I don't know whether it's unfortunately or fortunately, all these 3 sources are in very crowded, very complex regions. We have a lot of multi-wavelength counterparts, and the potential particle accelerators in this region. So at this stage, we cannot identify which astrophysical objects is corresponding for the ultra high energy gamma ray emissions. So let's have a close review of these three. So the first one is 1925, and the figure in the left is the LHAASO KM2A significance map. And we can see the white circle is this white circle and the purple circle is the position of the two famous high sources, 1825 and 1826. It seems for this source, the LHAASO, the peak of LHAASO emission, the UH emission is we cannot tell whether it's from this 1826 or 1825, and there are also these two, the positions of the two pulsars are marked as the black diamond, and on the other hand, there are also quite a lot of dense gas clamps in this region. The spectrum is shown in the right figure, and it can be fit nicely with both leptonic and hadronic scenario. And sorry? Okay, so both the and also it's not very constraining to the parent proton spectrum. Both Broken power law or power law with exponential cutoff is allowed. And for 1908, the situation is similar. We have pulsars, we have supernova remnant in this region, and the position and is more or less inconsistent with the Hess measurement. We also have dense gas for the hadronic scenario, and spectrum of this source is a little different. It's for this source, it seems a broken power law is favored than exponential cutoff power law. But still, both the leptonic and hadronic can fit this data well. And for 2226, we also is consistent with the position is also consistent with the former Veritas observations. And the spectrum is still the same, can be fit well with both leptonic and hadronic scenario. And one common thing for this resource is maybe we should I should mention here is we see this measurement of LHAASO. I mean, spectral measurement of LHAASO is in good agreement with Hawk, but both of Hawk and LHAASO data points seems to be a little higher than those measurements from the imaging Cherenkov telescope arrays. So maybe this is a kind of issue we should investigate later from the experimental point of view. And on top of those 12 bright sources, we also have detected two new sources which are not reported by former TeV observations. And the first one is 0341. And the spectrum, the data point, the gamma ray emission extends to more than 200 TeV. But on other wavelengths, we do not have a clear counterpart. And in this region, there's also now pulsars, or there's one pulsar, but it seems quite far from the peak of the emission. There's one corresponding Fermi source, but this source is also unidentified, and the spectrum is quite soft. In fact, it's very soft, about 1 GeV. It looks like a pulsar, but there's no position reported. And another one is J2108. This is the situation is also similar. We don't have any other counterpart in this region, but there's a quite soft Fermi source. And another kind of interesting source for LHAASO is the pulsar-related source. We all know that pulsars can produce GeV position emissions position through current radiation. And at TeV energy range, the pulse emission are also observed. Of course, this origin is not very clear. For example, this Felix in their 2012 paper, they argue that this could be the inverse compton emission from the cold pulsar wind. And the pulsar wind, the nebula itself, is also a very effective gamma ray emitters. On even larger scale, recently the Hawk collaboration, they discovered a new type of gamma ray source, so-called pulsar halo, and this I believe to be illuminated by the electrons escaped from the mid-age or old pulsars, and they interacting with the ambient radiation fields to produce such a very extended gamma ray emission structures. And for pulsar wind nebula, a crab, of course, is the most special one. So LHAASO, of course, detect this source. In fact, we use this source to calibrate our PSFs and the performance. This for LHAASO itself can measure this source in energy range for over 3 decades. I mean, it's both, we use both LHAASO WCDA and LHAASO PM2A, and the measurement can be extended from less than 1 TeV to more than 1 PeV now. And even above 400 TeV, the PM2A detected crop for more than 6 sigma. And in fact, the measurement, the spectral measurement of crop already we get some very interesting results. For this source, we detected more than 1 PeV photons. So if it has a leptonic origin, as in other pulsar wind nebula, the corresponding parent electron should have an energy of more than 2 PeV. And if we look the ICD carefully, we found that the simple one-zone model can fit the data very well, up to more than 100 TeV. But there are some hint of deviation of this one-zone model in this very high very high energy end. I mean, above several hundred TeV. It seems there are kind of in our published data, there are already a lot about 4 sigma deviation. And another thing is that from the measured ICDs and from the highest energy photons, we found the acceleration efficiency, which is defined as the average electron field to the average magnetic field can be as high as 15%, which is 1,000 times than that in the superresonant shock. And as I mentioned before, we also found the possible deviation from one-zone model, and probably this is a hint for another leptonic component or even hadronic component. Of course, we need to wait for the accumulation of data to clarify such kind of interesting issues. And in addition to the measurement of Crab nebula, we also detected a new pulsar halo. This is the third pulsar halo in addition to the former Hawk detection of Jaminga and Monogem. This is the this is also called this LHAASO J0622. From the its morphology, they obey this kind of predictions, assuming the diffusion of and the cooling of electrons very well. And we also have the nice measurement of spectrum up to 100 TeV. So before is some already published results of LHAASO collaboration, but of course they have a lot of to-dos, a lot of things, a lot of future tasks they need to finish. So one of the most important scientific objective is, I mentioned already, is the so-called pivotal hunting. So for now, the best candidate is in the 6 signals region. We already found 1.4 PeV photon in the region. If these photons are really from the hadronic process, this means this signals region, they harbor not only pivotrons, but probably even super pivotrons, which can accelerate protons to more than 10 PeV energy range. So in fact, signals region is long before it's regarded as a quite good candidate for the pivotrons. For example, this Andre, in his 2014 papers, they discussed the possibility of the acceleration of particles in the superbubble environment. They argue that the most efficient acceleration site is the supernova remnant shock colliding with this massive stellar wind. And in these regions, the particles can be accelerated even to more than 10 TeVs. And here is the of course, in their papers, they are discussing this Western Road 1, but the signals is a quite similar system. And in our Felix and I, in our 2019 papers, we also collected the former GeV-TeV data. And we found for signals, at that time, we only have the measurement of ARGO and up to several TeV, but there is no sign of any cutoff. And for now, we have LHAASO collaboration of more than 1 PeV photons. In fact, LHAASO already have a very nice measurement of spectrum in this region, and the spectrum can extend very nicely from GeV to PeV ring. It's a 6 order magnitude. And we are still waiting for the accumulation of data, and especially we are waiting for the WCDA results and after that we can present the detailed physical analysis to investigate whether this source they contain the most promising galactic pivotrons. And another thing is this WCDA. We are working hard on WCDAs, and in fact, nearly all this published results are from this KM2A array. But the WCDA itself is also quite powerful, especially at lower energy range. In fact, for now, this is the map I showed here is the preliminary WCDA significance map of the galactic plane, and as it seems, we have already seen all the Hawk sources already, but we are working hard on the improvement of this gamma p separation, on the angular resolution, on the energy reconstructions. And I believe in the near future, we should have a release of a lot of nice results in this a little lower energy range. And another thing I want to mention is the LHAASO, as I showed before, the sensitivity curve is the sensitivity of LHAASO is unprecedented, above 20 TeV, so it's an ideal pivotron hunter. But the disadvantage of such kind of EAS detector is the limited angular resolution. As I showed before, it's 0.3 degrees above 20 TeV, and even above 100 TeV, it can only reach about 2.2 degrees. And this may be not good enough for some kind of scientific studies. For example, as I mentioned before, a lot of these bright sources are in very complex and crowded regions. Here is the example. It's an example of 1908. In fact, these regions, we know they contain 2 bright pulsars and 1 supernova remnant. And in fact, it's possible that the high energy gamma, ultra high energy gamma rays are from several of these sources. But and this in the left figure is a kind of model input. And but if we seen such kind if we observe such kind of complex region with LHAASO, we can only see the middle panel. So it's in fact it's quite similar to what we're seeing now. We cannot distinguish where is the source. But if we have a better another instrument with a better angular solutions, for example, if we have this telescope telescopes with the angular resolution of 0.05 degrees, we can in fact distinguish these two sources. So this means the angular solution, in fact, is quite important to locate the source, and then only after that you can investigate the acceleration mechanism and for example, this radiation mechanism and particle transportation, such kind of physical studies. So the option is that we of course we are seeking for strong collaboration with the existed chemical telescope collaboration, such as MAGIC, Veritas, and HAAS. But another thing is we also we now also want to try to build another chemical telescope arrays at LHAASO site, and because we want to gain a strong synergy with LHAASO, so we concentrate on this high energy range above 10 TeVs. The current designs we are trying to using 6-meter telescopes, and we want to build 32 of them, and in LHAASO site. This means another interesting thing we can do is that we can use this muon detectors of LHAASO to increase the gamma P suppression power of IICTs to achieve the better sensitivities. Of course, we have LHAASO already, so we don't need to do survey. With such kind of facilities, I expected to only do a deep scan, deep observations of the specific sources. So here we compare the LHAASO sensitivity and our current design. This red curve here is the 500 hours exposure and we see that at 100 TeV, this kind of facilities can provide a comparable sensitivity with LHAASO. So we expected such small telescope arrays can provide this good synergy with LHAASO. So I think the time is okay. So this is my conclusion. So LHAASO already showed great power in gamma ray astronomy, especially in the Pevatron hunting. And we expect that we have a lot of important results. For example, in Cygnus region will be released soon. And of course, there are a lot of future tasks for LHAASOs. Here, what I covered is, in fact, is quite limited area. Only, for example, the diffuse gamma emissions and the high energy transient and the direct measurement of cosmic rays. And all these are ongoing in the LHAASO collaboration. And of course, the WCDA itself will also release an interesting result. For future, we are going to we are trying to build this small telescopes arrays in LHAASO site to provide a good synergy with LHAASO for more detailed morphology study. Okay, so this is my talk. I stop here. Thanks.
Thank you, Ruizhi, for nice presentation. So we start questions. So I see Jamie. Please, Jamie.
Thanks, Felix. Thank you very much for a nice talk. That was really, really interesting, really exciting work. I was wondering what cameras you're planning for the Air-Cherenkov telescopes. How many pixels and what's the field of view?
I think we are in the prototype now. It's we are using this traditional PMTs, but later we are going to use silicon PMs, of course, to introduce this duty cycle. And the current design is about I think about 800 pixels with a field of view of the 6.4 degrees. I mean the diameter is 6.4 degrees. Yeah.
Thank you very much.
Rashmi?
Hi, Ruizhi. That was really excellent. Thank you. That was fantastic. So I had a question about the spectrum that you showed for several sources, where the LHAASO spectrum and the IACT spectrums didn't quite match up. And it was not just an instrument, it was all of the IACTs, Veritas.
Yes.
Do you have kind of an understanding? I mean, it can't just be an instrument or analysis.
No. I don't know the reason. The only thing I can guess, but this is just guess. You know, is the background. I mean, the background method is different for this LHCT and ES. Probably. I mean, this maybe what I guess is is that possible? The source is this source is actually larger than what is seen by IACTs, and they subtract they subtract some. I mean, there are some of their off regions are in fact are still in this inside the source, so probably they subtract more, but this is only guess. I don't know. I think we probably we should have a monitor. I mean, kind of joint analysis on the same sources between these two, because you see, for example, this one is this Hawk and LHAASO. They two seems match each other very well, but both of them are higher than this IACTs. Yeah, this is a kind of mystery for me. I think we need to do something to clarify that.
May I intervene? It's good. I think we should study that. I'm in charge for people, and unfortunately, I cannot tell you too much. But it seems everything will come. Mystery will disappear. So, and I think
so this means there are some
are correct. It looks like
this means there are already some kind of activity inside HAAS, right?
Yeah, so that was his ongoing activity. I cannot tell, but I mean, hopefully this mystery will gone soon. So yes, there are. So sorry, I'm looking. I think it was Massimo. Massimo, please.
Yes, thanks, Felix. Thanks, Ruizhi. It was a very nice talk.
Thanks.
So I have a question about J2108. You showed a slide. So the question is, you associate, exactly. You basically associate that cloud that you show with the white contours based on the fact that the other one that you identify in the velocity spectrum, you say it's too big. But looking at the surface brightness image that you show of that other much brighter peak, actually, like the brightest emission, it's really within the LHAASO upper limit. So, I mean, I was wondering, can you completely exclude the association with the other cloud? And maybe even energetically, I don't know, it doesn't make sense. It adds up to like 100% of the of the energy that you would expect. That was the question, because really, by looking at that image, it really seems like the peak of that emission is coincident with the LHAASO emission. So I was wondering if you also had done energetic considerations there.
Okay. I'm not the corresponding author of this work, so yeah. But I think the problem is that LHAASO itself has, as I mentioned already, is angular resolution maybe is not good enough to claim to do such kind of detailed claim. Yes, I will ask those corresponding authors whether they can exclude the association with gas. Yeah. Thanks.
Okay, thanks.
Petra, please.
Yeah, hello. Thank you for a very nice presentation. Yeah, so since you showed the 1825 region, I actually had a question. Is this compared to the, for Hawk, in the comparison to Hawk, is this from the first publication with the high energy catalog that Hawk published, or is that the AppJ letter later that resolves 3 sources?
Okay, let me check. In fact,
and then my suspicion is that it is the first publication, and that leads actually to my actual question.
Petra, it is the first one, I think.
Yeah. Okay.
Okay.
Yeah. So my question is actually based on that. So Hawk resolves 3 sources in this region, right? 1825, 1826, and then source in between the 2, essentially. So my question is, you mentioned earlier that the resolution of LHAASO is somewhat limited, right? Especially for KMTA. Yes. But it seems like you're already doing some multi-source fitting in the Cygnus region, for example, right?
Yes.
And Hawk might have a slightly better angular resolution at these energies than LHAASO does. But I think, so I was wondering, is there any potential to resolve 3 sources here, for example? And that holds for any, the 1908 and so on. What's the progress on that? Because it seems to me that even with 0.2, you can achieve quite a bit by doing multi-source fits. Yeah, what's the status of that?
Thanks. This is a very, very good point. Thanks, Petra. And I think for now, one thing is that for morphology study, we want to not only this angular resolution makes sense, but also the statistics. So if we for Chem2A, the PSF above 100 TV can be as good as 0.2, but for morphology study, probably we need more statistics. We should do it from 40 TV, and at this energy range, the PSF is 0.3. Yeah, it's 0.3 degrees, and this is sigma. This is also not R68. So I think we are not at least for this 11 months data, we cannot separate the multiple sources in this region. But probably I mean, after some accumulation of data, we can try maybe with a higher energy range. Yes. And another thing is that in fact after these several papers, I would say the most of the manpower in the last collaborations are focused on the so-called this acceptance check of this whole project, because this is LHAASO itself is not only a scientific project, it's also a infrastructure infrastructure project that's sponsored by this the government or something. We have to there are the routines. You have to finish this acceptance check, but it's already finished. I mean, the full array is the construction is finished, and it's the acceptance check is finished, and we now can put all the manpower to such kind of detailed studies. Yes. Thanks.
Yeah, thanks. This is really great, by the way. I think it's important to do multi-source fits. And as you said, it's important.
Exactly.
With LHAASO and also IACT. So looking forward to the results.
Evgeny?
Out of curiosity, I would like to know something about instruments capabilities. First, what about variable sources? Are you limited somehow in studying variable sources?
For variable sources, I think the main facilities inside LHAASO is this WCDA, because it threshold. But as I mentioned, this WCDA, now we are still working hard on this energy reconstructions. So there's we have some follow up with this GRBs, but there's no detections yet. Yeah.
JRB is probably not the best candidates for LHAASO. They are too far away.
Yes. Too far away, and for WCDA, the energy threshold can be lower than 1 TeV, so it's still possible. But for KM2A, of course, it's not very easy. For KM2A, it's designed for gamma rays more than 20 TeVs, so it's not for extragalactic sources. And because even for these nearby sources with such high energy, it's not easy to study the variabilities. Yeah, but WCDA would be quite powerful.
Okay, we have still.
And then what about the possibility? Felix, can I continue? No?
Evgeny, could we just postpone? I mean, just.
Okay, then second question is it possible to see some signal from neutrinos that are coming from below through Earth?
Yes. There are some kind of ongoing activities. We are using this very high zenith angle events, but this is not from the bottom of the Earth. We are using this large zenith angle events to see whether there are possible detection of neutrinos. But I guess this would be still quite difficult.
Okay, thank you.
Okay. Andrew?
Okay, just to sort of following on in the theme of Evgeny's question, actually, about like what the instrument might be good for beyond what you said. Of course, you keep throwing away those cosmic rays, but you might also study them. And I was wondering if there must be groups involved in LHAASO that's thinking about studying the cosmic ray. I mean, you could separate the mass groups, of course, because you've got quite good muon measurements. Yes. And then you've got the angular information as well. And if you can separate them on a mass by mass, on a shower by shower basis, the cosmic rays, you might do anisotropy studies on a rigid, on a mass by mass basis of cosmic rays. Are these efforts being done?
Yes, there are ongoing activities inside the collaboration for such kind of studies, the direct measurement and this on the spectrum, cosmic spectrum, and mass composition. And in fact, we have some preliminary results, but because my talk is concentrates on this gamma astronomy, so I didn't talk about those steps. But there are already progress in that field, and I think the problem is still I mentioned this in LHAASO experiments. We do not have enough manpower to do this detailed scientific research work, but from now on, I think the progress will be faster. Hopefully they can release the results of the measurement of the spectrum and mass composition soon. In fact, it's already there. Yes.
Okay, very exciting.
Yes, they have quite interesting results on this knee region. In fact. Yeah.
Well, I was going to say the reason I'm interested because below the knee we know there's the swing in the phase of the cosmic rays and the amplitude, and we'd like to decompose that into components of mass groups. Yes. But very interesting. Thanks.
Okay, it's really good. Very we are following the time schedule. Also, we will continue questions, but now maybe we decide for the next half an hour. Maybe not to focus on 1 or 2 or 3 topics. So what I would suggest, because there was questions about angular resolution, and that is clear that LHAASO is extremely powerful, has everything, almost everything except for angular resolution. So in that sense, it's really very important to have this. Petra mentioned that Hawk has a bit better resolution. It's true, but still it's not sufficient. So clearly Cherenkov telescopes are critical. And to resolve, and I, again, unfortunately cannot tell everything, but you're looking at the LHAAS, we see that power of resolution for some.
Crab and the SNA results, right? Yeah.
Crab also 1825, 1826, or this, they are coming a lot of interesting results. Now, So we could talk about this a bit. I mean, about this, how to organize, I mean, this collaborate with Cherenkov telescope collaborations. At the same time, you mentioned this this array, planned array, just on the site of Cherenkov telescope. So we could discuss a bit if you, because Ruizhi is actually is a leading initiator of that array. So, or we initiator, one of the initiators, let's put in that way, politically to be correct. But so he could answer to these questions. And another second, I suggest we discuss is the Crab Nebula. It's extremely interesting result. And the problem is the Crab paper didn't appear in ADS.
Okay.
And we didn't put it on AstroPH archive. So I think 99% people don't know about that paper, which was published in Science. So that is a bit very strange. So we could a bit discuss Crab, I suggest, because it's very interesting results. And I see Ruyo is here. I hope still is here, right, Ruyo? Ruyo Liu. So Ruyo contributed a bit to that. So maybe we also Ruizhi and Liu could discuss this science paper, because there are a lot of interesting things. Just Ruizhi mentioned that a bit. This hadronic, leptonic, that could be good to discuss. Now, but let's go to your this array, Ruizhi, you put here. This so, and then you showed this sensitivity curve. Could we just look at that?
Yeah. Okay.
So this is blue one is, and then black is, what is the CTA? CTA is a black. And that is,
yes.
So I see better.
The city north, this is not city south, of course, is better
Yes.
at high
But
energy.
still, I could guess reason is the reason that this muon rejection?
Yes, the muon rejection, they provide some improvement, but I think we also, because the city nodes, they do not have SSTs, so they're not very big at high energy.
So you mean also area, but it will be small also to compare, but still, I think what you mentioned is extremely powerful addition to Cherenkov telescope technique, this muon rejection about 10
especially a higher range, above about 50 or 40 TVs. Yeah, it's quite.
I can see because even you have the huge area, 1 square kilometer, but still you go linearly above, so it means you are background free regime above 10 TV, right?
10 TV probably not, but it can still provide a better rejection power than ICTs itself. Yeah.
Yeah, I mean the right wing of the sensitivity. When it goes up, it means background statistic is more important.
Yes, that's true. Yeah.
And that is even you go so low. So it's very interesting. I mean, just if it's could be interesting really compare with without muons and with muons to understand what you could add. Okay, this is one, and then now there are LHAASO people here, Veritas, I don't know, Magic, so could just maybe discuss this with, I mean, the sources you have and LHAASO. We already discussed there's some conflict, tension between data, but what Ruizhi described as a mystery, and that is, so that is coming actually soon. All this stuff to discuss a lot. So I think the Cherenkov telescope current instruments, Veritas, Magic, and even LHAASO could contribute a lot to this resolution of sources.
Sure.
If they go, of course, they could not go beyond tens of TV, but at least above 10 TV, something could be resolved. Okay, so it's may I ask another question, Ruizhi, about this WCDA? That what you said is very impressive. You said that you detected almost all Hawk sources just for.
Yes, I think so. I don't know whether this is correct.
Well,
claim, yeah.
even half doesn't matter. I mean, just
Yeah,
exact
yeah.
number, but it's so quick.
Yeah.
And do you have 100 GV threshold?
No.
It's about
I
1
think
PV.
I think our situation is similar to Hawk at the beginning. We are still trying. We still need time to understand this detector itself. And for now, we don't have the reliable energy construction as that in Hawk at the beginning. So I think the map I showed here is we only cut on the N hit. I think it's N hit. Maybe it's kind of about 1 PV significant.
Yeah. But it's nominally should go to 100 GV, right?
Yeah, the design, the original design is I think at least 200 or 300 GV should be detected. Yeah. So Petra.
Yeah, just real quick. I was wondering how, speaking of Hawk and WCDA, I think, yeah, you're right. A lot of the challenges are the same. How do you distinguish sources for this when you say you found? So you're probably referring to a rather simple method that Hawk so far has used to produce catalogs, like just looking for like separations and dips and so on. Are you using that method, or are you also trying to use multi-source fit? I keep harping on that, but what are you using to identify sources? Yeah.
I don't know. I should ask how. In fact, I think he's leading that kind of studies.
Okay, it was just a question. Maybe I should ask how.
Yeah.
Okay, thanks.
So coming to this 100 GV it achieved, that was the question of Evgeny Derishev about variable sources. In fact, that could be very powerful then if you achieve 100 GV, even for extragalactic sources. I mean, not only extragalactic, also for even GRBs. So that could be extremely powerful actually for variable sources.
Paul is asking a question.
Yes. I can see.
Paul?
Yes. Hey.
Yes.
Just wanted to comment about this mismatch in between.
Okay, thanks.
Those things. So I understand that the mismatch is in the whole energy range, or is this particularly visible at highest energies?
Especially
but for KM2A, I think if we see this map, it seems in comparison with Hawk, the discrepancy between Hawk and LHAASO, Hawk and HAAS seems to be more prominent at high energy. But because we have not only LHAASO KM2A to begin, alright, its threshold is 20 TeV, so we don't have this energy. This trend depends on energy. But if you look at this comparison with Hawk, it seems getting worse at high energy.
It gets worse at high energy. So I was thinking if that would be because you are just using off regions which do have some photons coming from the actual source. Probably this may affect, this could affect the whole energy range. So the normalization that at some point is similar in the different instruments, I'm not sure that this would affect. There's another way, and I think that it was tried in HAAS and probably in other EACTs, which is an on-off method in which you take off data from another field of view, which is presumably empty. And in principle, this then allows you to take, as far as the source enters in your field of view, then you can take an off region as a background, and that would be immediate to see which would be the changes in the EICT spectrum.
Yep. Yeah, but this is very expensive, right? You lost half of your observation time.
Yeah, but as of today, we have plenty of archival data on anti-patches of the sky. So this could be just a matter of. There was also other methods. I mean, this cube method that may work as well. I mean, adding sources in a model-dependent way, but somehow it's a bit experimental still in the ACTs.
I see.
I had another question unrelated to this, but related to variable sources and binaries in particular. In the TEPA this year, it was reported and discussed that LHAASO detected 1.5 or 1.4 PeV gamma rays from 2032.
Yes.
This 50 years period binary. Is this, can you confirm this? Is this just, I mean, do we have photons in between?
Yeah, but it's I would say the photons, the position, the direction of the photon is quite close to the binary, but it's also quite close to signals OB2, and also quite close to signals X3. So it's hard to tell which is the true source of this specific photons. But the spectrum of the binary is 2032. They cut off much earlier than that of the spectrum of cocoon. This is also found by Hawk. We found the same thing. Yeah. So if we take this into account, it seems probably this is not from the binary. But no, we cannot. Of course, we cannot exclude completely. Yes.
Okay.
Petra, do you have another question, or is just?
It's a comment on the previous question from Paul. So I think there are two things going on here with the discrepancy in the spectra. Number one, it's the multi-source fit. It changes the spectra quite a bit, and that's why I was asking earlier if LHAASO could resolve it. I think, and yeah, maybe like you say, number one, it's a matter of effort, having enough people working on it. Number two, it's a matter of what the statistics is there, right? And the more statistics you have, the better you can do multi-source fitting. So that's one thing that's going on. And then the second thing is, I don't know if you're aware of that, there was a combined Hawk-HAAS publication where HAAS was doing a galactic plane survey with a slightly different background method that favors the detection of extended sources. And in fact, there HAAS did detect some sources that were previously undetected, that Hawk had seen, but HAAS hadn't. And I think there were 7 sources that Hawk claimed, and then HAAS looked at them again with this alternative background method, and they found 4 of them that they hadn't previously seen. So I think, again, this emphasizes, right, how important it is that IACTs and PDAs really kind of make a combined effort, you know, to look at the data in the galactic plane. And I'm happy to post the if for those of you interested, I'm going to post the link to the Hawk-HAAS paper.
Thanks, Petra.
In the chat.
Yeah, that was partly the mysteries have been solved, but tensions, they are still there. But it's clear that tendency that if you go deeper studies, then they should agree each other. And that interesting point is that these Cherenkov telescopes and the LHAASO or Hawk, they are really necessary to have both, because it is not a general statement. It's just 0.2 degree, and those sources have sizes about 0.2, 0.3 degree. So in that sense, 0.1 degree, or is just not general statement, better to have a good resolution, that really necessary to have resolution better than 2-3 times better than HAAS, Hawk and LHAASO. And that is exactly Cherenkov telescope could provide. So some good compatibility. There was a Sabrina.
Yes, I wanted to confirm what Petra was saying, that multi-source fitting is making a difference. And we are going into this as well with ICTs. And this maybe won't be a longer mystery.
No, it is.
But Sabrina, if I remember correctly, several years before in this, for example, in the case of 1825 and 1826, we already did this multi-source in HAAS with HAAS, isn't it?
Some more exciting are coming, Ruizhi. Yeah,
Oh,
we did it a couple of years ago. That's true.
Yes.
That's true. But yeah, something, more exciting is coming up.
Okay. Good news. Yeah.
Exciting in the right direction. So in the sense that really you need Cherenkov telescopes. I mean, then you could solve things. So, and there was another question. I don't know who was. There was.
Roy?
Now it's free. Yes, Royo.
Hi. I just want to add a comment on this J1825. So I think the HAAS data here is only for J1825 minus 13.7, right?
Yes.
If we include, if we include 1826 here, this difference will be smaller. But still, LHAASO
you're right.
Slightly higher.
Sorry, I forgot to mention. You're right. Yes.
Real, but better to wait. I think it's just not to try to better to wait. I mean.
Okay.
I think I saw the
Luigi.
Luigi. Yeah, Luigi.
Hi everybody. Thank you very much for the talk and the fantastic results. I have one question about these future small telescope arrays. You said that basically you plan to put 8 small 4x4 arrays. Would it be possible, in principle, since you are at more than 4,000 meters, to basically do the old Felix idea of 5 at 5? So basically one of these to become a sort of 3 at 4 at most. I mean, 3 semi-large telescopes at 4,000 meters. So to go on the other side of the LHAASO spectrum, basically at lower energy, exactly to be a sort of timing explorer as we previously.
Thanks, Luigi. This is a very interesting idea. In fact, we are thinking of such kind of possibility for those larger telescopes. But I would say probably this LHAASO site is not ideal for this larger telescopes because the weather in LHAASO site is not the best in China. And another thing is we want to so this is why we want to build this relatively cheap and fast telescope arrays, because it's small and everything there is technically it's not too difficult and it's relatively cheap. And we just want to build it to get the synergy with LHAASO, to concentrate on its very high energy domain, and for those larger telescopes, because of course they would be much more complicated and much more expensive. We want to put that in a much better site. We have several such sites in China, and another thing is we put this large array, this small telescope array in LHAASO site is that this if you want to get this very high energy, you need the large area of the array. You need at the level of 1 square kilometers, and this would, I mean, to get so much land, this a huge amount of money. So, but in LHAASO we already have this land, this one square kilometers. We just put there. So this is also from the economical point of view why we put this in LHAASO site. Yeah.
Also,
for this
perfect match to the objections of LHAASO.
Yes,
like,
yes.
So it's a part of LHAASO.
Yes, it's part of LHAASO. For this larger one, it's of course we all know it's very exciting. We probably, if we can finish the small ones, we will trying to on that direction. But that of course we will put on a much better side, yeah, to the optical observatory side. Yes.
Okay, thank you.
And
thanks,
Jamie,
Ruizhi. Yeah.
Jamie.
Yeah, I have a couple of different questions, really, if we're in the discussion section. I was wondering first if you've started looking for any variable sources in the LHAASO data. So that could be either known TV binaries or
yes, of course, yeah.
New systems.
Of course, yeah, we are searching for binaries. We are looking for this. I think on our side there is this RS 1529 and this is 61303 are all in LHAASO field of view, and we are trying to search for that. But for now, there's no detection yet. What I can say is there's no detection yet, both from this WCD and CAM2A. Yes.
But
yeah, they do seem to be quite steep at the higher energies.
Probably yes.
Yeah.
But there are also Markarians, Ruizhi.
Markarians. Yeah, I know. Yeah, Markarians, I know. Yeah. But yeah, I see. That's correct. Yes. Yeah.
M87 is pretty close as well.
I think the actual galaxy cells what we detect is only Markarian, right? It's only Markarian. But the WCDA, I'm not aware. But
no, M87, Ruizhi, Jamie asking.
It's also
M87. No, M87 is a perfectly in field of view, and that is in HES it goes 20 TV, 10 TV published, 15, so it's perfect source as well. But it's very weak source, Jamie. So
yeah.
It can flare if you're lucky.
Yes.
No, but
sure, of course.
Accumulate another 2-3 years, then it will get it. Yeah.
Yes.
And then my other point was a bit maybe speculative for discussion and for some of the longer term IACT guys to think about. There's a paper by Werner talking about the fundamental limits of angular resolution of the IACT technique, and I think that kind of cuts off at 1 or 5 TV or something like that. So I was wondering, what is the fundamental limit of angular resolution at 100 TV or at 1 PeV? And how close to that can you get with a Cherenkov telescope array? Can we reach, I don't know, arc minute imaging or something like this? It would be quite remarkable. I don't know if anyone has any thoughts on that.
Well, I can answer. You remember Werner 1 or 2 years ago was claiming that he can get better resolution with particle arrays than Cherenkov, but I understand he gave up with this. I think it was, but he was claiming at the beginning that it could be better than 1 arc minute.
Okay, so the information is there.
You ask him directly, because I don't know what happened. I mean, he's not claiming anymore that, so maybe that, okay. But there was a claim, and maybe statistics or some systematics. You could ask him directly. I think he had some note even somewhere. Yeah. So I just promised, I don't know that was we have time or not, discuss this crab, because I'm so disappointed. So much efforts in the crab, what is a heroic effort published in the science, and at the end, no one knows about that paper.
Felix, I think we find the reason why it's not in ADS. I think, I forgot to mention this to Jen, and probably I will write to him tomorrow and ask him to write a letter to his science. This is a problem of science, because I think they missed the comma of the between the author names, so you cannot search his paper
They missed a
this
lot of
any
things.
name.
You know, it appeared, they changed it to the paper and then put the old version as a paper and then they changed. So it was a lot of confusions, but now it's not even a DS. But maybe better to put archive. I mean that.
Sure. Yes.
Because
I
people
think
are
Roy can put that, right?
Yeah.
Roy, are you there? Still here? Probably you can put that on archive. Yeah. I don't know. I don't even know it's not in archive. Okay.
Well, can you put the link? Jamie's got a good suggestion. Just post it here.
Sure. Yeah. Let me try to find.
Yeah. And what are perspectives for crop? Maybe Ruyo, could you say that what is going to happen? Because
I first close the share on my screen and I will send the link. Yeah.
But I don't see Ruyo. Is he or not? No, he left probably, right?
Oh, he left. Probably it's too late. It's quite late in China now.
Yeah.
Okay. I'll try to find this science paper.
Well, we are almost out of time, so I guess we should have closed. But if people want to stay on to discuss, they're welcome to do that.
Yeah.
Yes, I think maybe Felix, we should thank Ruizhi again. That was really nice.
Okay, thanks, Rashmi. Thanks, Felix. Yeah. Okay.
Thank you, Felix.
Okay,
Should we close it for today? Thanks. Okay. Bye, everyone.
Thank you. Bye.
Bye.
Bye, guys.
Bye.
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 Thanks.
Bye.